Okay, welcome to grade 11 physics. Let's get rolling. We got a busy schedule today, so we're going to run through a bunch of things. Our goals for today are to go over fundamental and derived SI units, scientific notation, significant figures, orders of magnitude, maybe a little bit estimation, and some unit conversion. So this is going to be a bit of a busy one, maybe a bit long, but we'll persevere. All right, so when we talk about fundamental and derived units, okay, so there are certain fundamental units that we have chosen will be the base building blocks, and then derived units are built off of those fundamental units. So these are fundamentals, so mass, length, time, temperature, electric current, luminosity, and mole. And we will use the first 5 more than we'll use the last 2. So you should be familiar with the units of measure. So mass, kilograms, length in meters, time, seconds, temperature, Kelvin, and then eventually we'll get to electric current, which is amperes. Okay, so those are what we call fundamental units. We had to make a start or choose a place to start with our measurements. So this is what we start with. Derived quantities, they're combinations of the fundamental units. So something like speed, for example, is a combination of distance, or meters, per unit time, so seconds. Acceleration is another one. It's measured in meters per second. So you use a lot of derived units in all of your sciences. The one you're probably most familiar with at this point in time is your kilometers per hour or miles per hour, but miles per hour is not our metric system. Okay, so in IB, the units we use are a European format rather than the American format. I will switch between both because I'm familiar with both, I'm comfortable with both. So what we're looking at this here would be an American format, or North American format if you prefer. So kilometers over hours. Okay, now if we wanted to write it in more of a European format, we take advantage of our negative exponents. So a kilometers over an hour would become kilometers times hour to a -1. Okay, and I threw in the r just because we make sure it's an hour. Okay, so that little negative exponent just means it's moving from the bottom to the top location. Scientific notation and metric multipliers. I have these around the room. It's not a bad idea to snap a photo of this or download this. These are all the common prefixes that are used, and you should be familiar with them. Some are more popular than others, but these are the ones we want to try and make sure we know. So if you are into computers, you'll recognize things like megabyte, gigabyte, terabyte. Well, all of those little words in front of byte are an indication of how many there are. Okay, so mega is 10 to the 6. It actually means million. Kilo, you should be familiar with. Sometimes it's said a little bit differently. We say a kilometer, but it's also kilometer. Those would both be correct. And it's a unit of 1,000. Okay, so there's centi, milli, micro, nano, pico. Make sure you've got an awareness of all of those, and you can always go back and reference the table. There are little symbols. Okay, and you'll see this on the next slide, how we use those. 2 slides, I should say. Now, scientific notation. It's a way of taking very large or very small numbers that are perhaps too big or bulky to work with on a piece of paper or on a calculator, and it allows us to shrink them. Okay, so a number in scientific notation normally is expressed something like this, where you have some value a times 10 to some exponent that's normally an integer. In this case, you just have a b there. Okay, so the a is sometimes called a coefficient, the mantissa or the significand. I'll probably stick with coefficient just because it's a little easier. We'll say it's normalized when a is between 1 and 10. So you could see down here, if we looked at the number 350, you could write that a couple different ways. You could say 3.5 times 10 squared, 35 times 10 to the 1, or 350 times 10 to the 0. Those are all scientific notation. They're all correct, but the one that would be normalized would be this one. And you can see that the a value of 3.5 lies between 1 and 10. So that's what we call normalized. All right, so let's take a quick look at a couple of these. So after you've tried a bunch, it gets a little bit easier. So we're moving from standard decimal notation, so that's where you write the number out in its full entirety, to a normalized scientific notation. So we're going to travel in this direction. So 2 seconds would be 2 times 10 to the 0, keeping in mind that 10 to the 0 is the same as 1. I won't do all of them, but I just want to point out a couple things. 300 would become 3 times 10 squared. Now, what we want to keep track of is this decimal place. So if you notice, the decimal place here is to the right of the first digit, to the right of the 4. So if I count, we can call them jumps for lack of a better term. 1, 2, 3. There's 3 jumps to get to that location. Okay, so that's where you could find that exponent 3. Okay, and now here's your introduction to those prefixes. 10 to the third, which we saw was kilo. Okay, so instead of writing 10 to the third, you could put a K in front of the S. Okay, so these are all the same value, just expressed different ways. Okay, so there are 3 different ways to look at this. Okay, and it's worth stopping, pause the video here, and really read over this. This value here, this value here, and this value here are all identical. They just have a different way of being expressed. That's a really important distinction to know. Okay, I'll take a look at maybe one more here. Again, if we want to look at how many jumps we have to go, the decimal place is currently here on the standard form, and then we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's where this 9 comes from. If we have a small number and we're jumping the other direction, okay, so we're moving to the right of that 2, that's what you'll notice. It has a negative exponent, so it's going to make sure that 2 times a small number gets us back to the small number we started with. And again, let's do the last one. We'll just count the number of jumps. Again, I'm jumping to the right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be my new decimal place location, and you can see 10 to the negative 9. Okay, and if we look at that 10 to the negative 9, the prefix shortcut for that is nano, which is a little n. Okay, so now significant figures. This is an important part of your IA and your labs and those types of things. So we want to make sure we keep track of error in our measurement. Anything we measure has some type of error in it, so we're going to just chat a little bit about how we keep track of that. Okay, so a meter stick has marks every millimeter. The best measurement you can get by a meter stick is to within 1 millimeter. Okay, everything else is a little bit you're guessing. So the most accurate you could be with a meter stick is 1 millimeter. Okay, and different tools have different accuracies, okay, or different precisions. Significant figures. So if we look down below here, we can see we have a little ruler or meter stick, and we're measuring the blue line. So the 1 for the first centimeter right here, okay, we would call that the most significant digit because it's the main portion of our measurement. I also think of it as confidence. It's the number we're most confident in. And then as we move to this next piece in here, we can become a little less confident in it. And it becomes the least significant digit because we know the value should be somewhere between 1.1 and 1.2. Okay, and in this case you might say, well, it's closer to 1.2, so you might say the answer is 1.2. The 1 centimeter first digit we're really confident in. It's the most significant. The 2 over here we're a little less confident in, so it would be the least significant digit. So significant figures continued. A ruler is an analog measuring device. Now analog simply means it's not digital. Okay, so we have lots of different analog devices. So meters with needles, rulers, graduated cylinders, those types of things are all analog. Okay, and now you have the ability to estimate the last digit for analog devices. So if we return to our ruler, for example, here, and I apologize, these little highlighters here, and here, should be all bumped up a line. They didn't convert well, so if you want to slide those up a line, you can. So if you look at this one, if we try and keep a little bit more accuracy in our measurement, again, the 1 for the 1 centimeter would be our most significant digit. We now have probably a bit more confidence that we can go 1.1. Okay, and now we're going to be doing a little bit of estimating on where that red line falls. Is it 1.17 or is it 1.18? Okay, and so the uncertainty now falls on the 7 or the 8. Both would be correct, okay, because it's just an estimate, but you can only get so accurate when you are looking within those estimated ranges. Okay, now a digital measuring device, however, does not have the ability to estimate whatever the final digit is. So in this case right here, that's as far as you can go. You can't see anything to the right of that digit, so you can't guess, is it closer to the higher number or the lower number. So for this particular one, 0.1 volts is the most accurate and the most significant you can make this. That's the end of that discussion. Okay, so digital's kind of easy in that way. The last digit, boom, that's where you stop. All right, so this one here, this is worth a pause and take a look. These are the rules or guidelines for significant figures. I'll read them really quickly, but it takes a little bit of time of just staring at the numbers and looking at what's behaving, what's happening. So all non-zero digits are significant. So 3 non-zero, 4 non-zero, 2 non-zero. Okay, that one's usually the easiest one to comprehend. All zeros between non-zero digits are significant. So anytime these zeros in here are trapped, okay, then they're significant. You'll notice though that this one here is not trapped. So the significant digits are these 4. Down on the next line you have 2 zeros trapped within, and if you count up all of those digits you have 5 significant digits. Filler zeros. Okay, now here's where things have to be, you got to go a little slower. Filler zeros to the left of an understood decimal place are not significant. So that means these little guys right here. Okay, and I've done those two in green. So the understood decimal place, you'll notice there's no decimal place written there. Okay, so these two here, these two green underlines, are not significant. So the only significant parts are these two values and this one value. Now if I go down to the third example here, there's a decimal place that has been written, and that is a really big indicator. Please watch right down here. I'll scroll that up in a minute. When you see a decimal place put in there and there's a 0, okay, that means that both of these are actually measured and accounted for, so there are 2 significant digits, and it's all because that decimal place has been written there. That's a real big idea, something to keep track of. Can make questions a little challenging at times. Number 4, filler zeros to the right of a decimal place are not significant. So the filler zeros we're talking about are these two right here. Okay, this one right here. So just like we had filler zeros to the left of an understood decimal place, filler zeros to the right are not significant, so we only have one significant digit for both of these. And then lastly, all non-filler zeros to the right of a decimal place are significant. So non-filler zeros to the right of a decimal place. So again, here is that decimal place right here on the first one. Because that's written there, that's communicating that that is accurate to 2 decimal places, or to 2 significant figures. If it was only one significant figure, it would have just been written as an 8. Okay? 60.40, again, this is communicating that all 4 of those are important. And this is the last one's probably the most difficult one to keep track of. Okay? Okay, significant figures and calculations. Now, again, this one, I have this all around my room on paper. I highlight this one because it's a real easy mistake to make. When we multiply and divide values and we work with significant figures, okay, we're going to round our answers to the same number of significant digits as the quantity with the fewest number of significant digits. So there are 2 sets of rules. There's a multiplication and division rule, which is this one right here. So if you notice, for the first one, we're multiplying 1.2 times 2. This only has one significant digit. So if we multiply them together, we get 2.4, but then we have to round that down to one significant digit. Okay, and sometimes that can be really tricky. If you go through all of your calculations for the second one, you come up with a fairly long decimal. But if you look here in the original, there's only 3 significant digits, so you have to round this off. Anytime you work with pi or do divisions, you can generate some fairly long decimals. That's what these ones are like. And again, it's worth pausing and just take a look at how they came up with those values. Now the second one, and this is the one I always make mistakes on, so please watch for me making a boo-boo. Addition and subtraction, you round your answer to the same number of decimal places. Okay, so that's a big difference. Decimal places versus significant figures. So adding, subtracting, you're rounding off to the number of decimal places. Okay, I put a big warning on there because that's something that's easy to miss. So when we look at the first example here, this one here has 0 decimal places. So even when we add these two things together to get 3.2, we have to round it off to whole numbers, which is just 3. This one's tricky here. It just seems so counterintuitive. If you have 2,000 and you add 2.1 meters to it, because the 2,000 right here has no decimal places, we don't know how accurate it is. So we have to round this one off to, you can get it, right back to 2,000. So if you can imagine, you've taken 2,000, you've added 2.1 to it, but your final result is just 2,000. Okay, that's a tough one sometimes to work with. All right, so when we read something like a graduated cylinder, for example, or a thermometer, the first thing we want to notice is what are the little gradations, what is their value. So if we look here, we have 50 is on this mark, 60 is on this mark, and if you count the number of gradations, there are 10 within there. This little extended guy is 5. When we're reading something like this, we read to the bottom of the meniscus. That's the dip in the water. So if we count here, we have 1, 2, 3. So our value is going to be somewhere between 52 and 53. And you can probably make an estimate that it's closer to 53, so you might say something like 52.8. Okay, and that's about as accurate as you can read that. If you come over to the second one here, you have to be very careful. This marker right here is a 7. So these little gradations are actually worth 0.2 each. So this measurement here, this is 0.2, 0.4, 0.6, and 0.8. So we're somewhere between 6.6 and 6.8. And I'll just erase that so we can have a better look. So we might say that is 2, 4, 6.7 maybe? Somewhere around there. And again, it's the best guess you can make. This is your least significant. This is your most significant value. Okay, so if we bring these up, I should also point out that green slides come from IB tests. So these are actual IB test questions that you may have seen. Okay, so 5.28, we were pretty close on the first one, spot on. And then they went a little bit further with their reading. They went to 6.62. Again, both of those would be okay. Orders of magnitude, you will never have to memorize these, but they are handy to have sort of organized somewhere that you can look them up if you need to. So you can see a range of things from the mass of the universe being 10 to the 50th. This is quite literally beyond human comprehension. You can't really think about that number. It's just an abstract concept. Down to something like this, which you may not know is a Planck length or mass of electron. You're looking at 10 to the negative 31, negative 35. Again, numbers that are beyond human comprehension. In your mind, we just work with them. Now, an order of magnitude, though, is when we set up a ratio and we put one over top of the other. So if we're looking at something like this, find the difference in the order of magnitude of the mass of the universe to the mass of a quark. And you don't need to know what a quark is just yet. We'll get to that. It's just a really small particle for now. So if we set up a ratio, here is our mass of the universe divided by our mass of a quark. We have to watch our exponent rules. We are subtracting the exponents. So this is 50 minus negative 30, and you get 10 to the 80th. Okay, so the order of magnitude is the exponent value. So it's 80 orders of magnitude greater. Okay, and again, that's just beyond human comprehension. but it's things we need to know, especially for the IB folks. So here's again an IB question, and all of the information would be provided in terms of the diameter of the nucleus, the diameter of an atom. What you're responsible for is, do you know how to put it into, or put the values into the expression and then come up with what the order of magnitude is. So here are the two diameters. You put them as a division case. We subtract our exponents. We end up with 10 to the negative fifth. So the correct answer would be C. Okay, so unit conversions. I'm a big fan of this visual technique. I write a very definite top and bottom to my fractions. So if I want to convert 4 hours to seconds, this is the way I would set it up. I would have 4 hours on the top. Within 1 hour, there are 60 minutes, so this is a known ratio. Within 1 minute, there are 60 seconds. And the way I like to do this is the visual component is I can look at these hours here. One being on the top and bottom will cancel. These minutes here will cancel, and I will be left with just seconds as the units on whatever my conversion is. Okay? To actually make the calculation, we're simply going to multiply across the top, multiply across the bottom. So 4 times 60 times 60. Okay, so 60 times 60, 3600 times 4, that is 14,400 seconds. Okay, so that's how many seconds are in 4 hours. Okay, so that's a very handy visual technique. If you want to pause it and then try a couple here, just set them up, set up the ratios, set up so that things cancel. You'll find that most of these come apart pretty easily. So pause it here. Okay, so 20 hours. So the key with this is knowing where to put things. If you put 1 hour here and 60 minutes on the bottom, you'll notice the hours won't cancel each other out. Okay, so that would be an incorrect setup. What we want to try and do is make sure we have 1 hour on the bottom, 60 minutes on the top. These hours would cancel, and we would have 20 times 60. We would get 1,200, and you go, I wonder what units. Well, the only units that are left are minutes. So there is your answer. Okay, 60 minutes or 600 minutes to hours. Start with 600 minutes. We're going to use the same ratio. Now this time we're going to flip it though. So we're going to have 60 minutes on the bottom and 1 hour on the top. We look at the units. The minutes will cancel, so we've set it up right. And then we do 600 divided by 60, and we get 10 hours. Okay, and then lastly, 3 hours to seconds. Same process. And we will shortcut this in the future. We'll make it a little quicker. So 1 hour is 60 minutes. 1 minute is 60 seconds. You'll notice the minutes cancel, the hours cancel. I'm left with seconds, which is what the question requested. And now I just have to multiply across the top and bottom. So I have 3 times 60 times 60, and I get 10,800 seconds. Okay, so now if we wanted to convert 405 seconds to minutes, so you can see I have my 405 seconds here. I have the standard ratio. Okay, so I take my 405 and I divide it by 60, and I get 6.75 minutes. Okay, because these guys would cancel. And that's a correct answer. But what if we don't want the decimal? And this is where sometimes people get stuck. Sometimes people will write this as 6 minutes and 75 seconds. Okay, and that is incorrect. That is bad. We don't want to do that. Okay, so what we want to do is we're going to break out 6 minutes and 0.75 minutes, because if we added those two together, we'd get back to the 6.75. And then we're just going to convert this piece or portion of the minutes. 1 minute is the same as 60 seconds. These guys cancel. And when you times 0.75 times 60, you come up with 45 seconds. So this would be 6 minutes and 45 seconds. Now maybe you were comfortable enough with 0.75 being 3/4 and you could go straight to 45. That's fine. I'm interested in the process. Alright, so you want to pause it and try your own here. So we're going to try and write these in a non-decimal format. Okay, so we're going to try and get rid of those decimals. Okay, so we have 4 hours for sure, and then we have 0.3 hours, and we're going to try and get rid of that. So we'll start with minutes. So 1 hour is 60 minutes. So this would become 4 hours, and then 0.3 times 60 is 18 minutes. Okay, hopefully that makes a bit more sense. 5.875, we'll do the very similar. 5 hours, and then we're going to take the 0.875 hours and convert it. And then we just take the 0.875, assuming I can punch it in right, times 60, and we come up with 52.5 minutes. But there's still a decimal in that, so we may not be happy with that. We can split the 0.5 minutes off, just like we did in the previous line, and repeat, or we can recognize that 0.5 of a minute or half of a minute is 30 seconds. Okay. Let's go. Does the ratio conversion strategy work for other units of measurement? It works for all measures of unit or measurements units. Oh boy, tongue-tied. It works for areas, for volumes, for everything. That's what's really cool about this. So if you were given a new ratio here, 1 inch equals 2.54 centimeters, you could take this from 5 meters all the way to feet if you really wanted to. I'm just going to slide it over a little bit. So I might do something like this. 5 meters. 1 meter is 100 centimeters. I better move that up, I think. We're going to run out of space here. Okay. And then, so right now I am in centimeters. Then I might go to 2.54 centimeters equals 1 inch. And then I might have 12 inches equals 1 foot. Okay, and it starts to get a little messy, but what's nice is you can always check. Meters, meters gone. Centimeters, centimeters gone. Inches, inches gone. I am left with feet, which is what the question asked for. And then I multiply across the top. 5 times 100, 500. And then I divide by the bottom, so you might need a bracket. 2.54 times 12, and you hit equals, and you get 16.4 feet. Okay, so 5 meters is the same as 16.4 feet. And then the last one here, and then I think we're almost done for the day. 12 meters squared to feet squared. So you would start with 12 meters squared. And I might just give you a new ratio here just so this goes a little faster. 1 meter is equal to 3.3 feet. So what we might say is, well, 3.3 feet is equal to 1 meter. But there's a problem here. You'll notice this guy right here says I have 2 units of meters. So we would need to introduce another group of our ratio. And now, when I go to cancel, there are 2 m's, m here, m here. And some of you will notice you could have just squared that bracket. So this is going to be 12 times 3.3 squared feet squared, because feet and feet together. And then we can just punch that in. So 12 times 3.3 times 3.3, and we should get 130.68 feet squared. And then depending on how accurate we are with these values, we might just round that off to 131 feet squared or somewhere thereabouts. Okay, so that's a long day. Appreciate your time. Thank you for that. There is a task to work on, and we'll see you tomorrow.